I'm just trying to show you how to fit in the largest triangle that you can fit, an isosceles triangle, within a circle. And I'm trying to show that, prove what type of triangle that would be and what size. And the interesting thing is that this, whoops, this does not rely on the radius, believe it or not. So let's start here. So it says find the largest isosceles triangle that will inscribe onto a circle. So here I put a circle and then I put a triangle, and then you can see I dropped this main diagonal here. It's called a bisector. That splits the angle into theta and theta. And so you can see that in the way it's bisected this line so that PC is congruent to BP, you see. And so what we're going to do is, first of all, we know that from this point here, so I can just do it from here. Let's see, from this point here to here, maybe I'll just make it a little kind of like that, and then use that so that this, from here to here, you can see, it's hard to see, but from here to here, that's R. Maybe I can do a blue. You see, that's R. And here's another R. See it? All of those are R, radius. And then what you're going to do is construct something that goes from here to here. Do you see it? It's like it's another perpendicular bisector. And it's a 90-degree corner, right? So so now we see that bisects this so that AM and MB are congruent, right? So if we want to talk about AM, right, that's the measurement from here to here, then I'm going to take the cosine of theta, right? The cosine of theta would be AM divided by R. You see it right here? AM divided by R. So if I solve for AM, then AM is equal to R cosine theta. But because this is congruent to this side, that's also, down here is also equal to MB. You see, MB and AB are both equal to R cosine theta. So if you want to know what the distance from A to B is, see, why, it's just R cosine theta twice. And then and then AC, which is this angle from here to here, you see it? That one right here, that guy is the same length as 2R cosine theta because it's an isosceles. By definition, an isosceles triangle has at least two sides that are congruent. Okay. So now that we got that part, let's move up just a little bit here. So I got the definition of isosceles triangle. Now what I'm going to find is that, well, we know that AC is what we said here. AC is congruent to AB is equal to that, right? Now find BC. Well, BC would be the base of the triangle, you see, from here to here. And first we'll find PC. So if you take a look at this distance right here, just from here to here, see it? And you look at this angle here, so if you want to take the sine of theta, so BC, well, let's put it here. Let's start with here. So BC is just going to be equal to 2PC, right? Because it's also bisected in the middle of that line. So PC is going to be equal to the sine of PC divided by the hypotenuse, but we know that the hypotenuse is R 2 cosine theta. So another way of writing PC is to just call it 2 times R cosine theta sine theta. See that? And let me move up a little bit. And then we're going to go up here. So now we have BC. So BC is going to be 2 times one of these PCs. So that's going to end up being 2 times R cosine theta will give us a BC that is going to be, let's see. Yeah, so BC will end up being 4 times the cosine theta. Now we know that the triangle is 1/2 the height times the base. But BC is in fact the base of that triangle right here. See it? BC. And so now what I have is I have an area function that's dependent on theta, and so what that's going to be equal to is I got the 1/2. I haven't calculated h yet, but I know that the base is equal to 4 times cosine theta sine theta. Okay. Now how about the height? Well, the height, if I come down just a little bit so you can see the picture, the height is AP, you see. But I know what PC is now, and I know what the hypotenuse is. It's 2 times the r cosine of theta. That's the hypotenuse of this guy right here. So if I want to take then look at the cosine, okay, so AP would be the cosine of theta would be AP divided by the 2r cosine theta. So here I have a cosine, you see, of theta of the line segment AP divided by the hypotenuse. That's the definition of cosine. And so if I solve for AP, I know what my height is. My height is going to be 2 times r cosine squared of theta. So now I can do my area function. So I know that this guy is 2 pi r cosine theta. That's the height, right? And then this is the base. And I can see that the 2 will go into 4 twice. So that'll end up giving me the famous right here is going to be that my area function well, this function as a function of theta, right? So now I'm going to take the first derivative, and when you take the first derivative of this, then you can set it equal to 0, and that'll start finding your critical values so that we can optimize. So now we're going to take the derivative of this, and that's what we want to do. So this would be, actually this is, I'll get rid of this ping right here because it's just there. So the compressed form is, 4 r squared, because you can see that we have an r over here. You see it, an r here and an r here. So we have the r squared here and then the cosine cubed. And I just factored out the 4r squared. There's 4r times r. All right, the 2 divides out with the 2, so there's no problem. So that's what I have. Now I'm going to use the product rule, you see. So I'm not even going to look at this because none of this has to do with theta. So I'm going to just pull out the 4, there it is, the 4r squared, right? But now if I take the derivative of the cube of cosine theta, I will get the chain rule first. So I bring down the 3, right? And then I subtract one of the powers, so it's cosine to the second power. Now I have to take the derivative of the cosine, right? And that's derivative of cosine is minus sine. And then I have to multiply it by this sine. So then I get sine squared theta, see it? And then I got cosine squared here, and 2 times cosine minus sine squared theta. So I brought this minus in front for now. So now I have all of this, and all I did was combine these 2 guys here, see it? And when I combine, that's how I got the theta cubed. Yeah? So let me go up a little bit more, and so you can see it more clearly. Okay, so now I got the cube section, you see? There. So then now I'm continuing to take the derivative. So I'm just combining terms, right? So if I got so what I got here is 4 cosine theta, and here I have cosine minus 3 cosine squared theta and sine squared of theta. See it from up here, and this is the 4th power because I got cubed, and this guy makes to the 4th cosine to the 4th power. So I still have this, and then what I did is I factored out a cosine squared theta, see it? So when I factored it out, I have this term and then this term. Now, in order to find the critical values, I'll set the derivative to 0, which is the slope of 0. So you can see that 0 is equal to the cosine squared of theta that comes from here, and this comes from here, see it? And so this is like two factors. Either this guy has to be equal to 0 or this guy has to equal to 0. So if we set this second term equal to 0, then we get this guy, see it? And if I set that equal to 0, and then I divide both sides by the cosine squared of x. So what I got left when you do your algebra is that the sine squared of x over the cosine squared of x is equal to 1/3, see? Because I divided by cosine and then I divided by 3. So it turns out that this is the same thing as calling it the tangent squared of x. So the tangent squared of x is equal to 1/3, and if I take the square root of the tangent, I'll get tangent, so I have plus and minus 1 over the square root of 3. Now this particular one is kind of easier because it's a famous triangle. So if I have 1 here and the square root of 3 here, and you use the Pythagorean equation, you'll say that square root of 3 squared is 3, and the square root of 1 squared is 1. So now I have 4, so the square root of 4 is in fact 2. So that works. And it turns out that since this guy here is, this angle here would be bigger than this angle here, because this side is 1 and this one's square root of 3. So it turns out that this actually is going to be, here is going to be 30 degrees, or what we call, we can just call it pi over 6, you know. So this has to be pi over 6, which is 30 degrees. And that's 90. So that would leave it, not that you need it, but that would leave you pi over 3, because they have to add up to 1 over 80. But even if you didn't know that, you could take now that you have this guy right here, right? And let's look at just the positive guy, not the negative right now. So now what I have is, I have the tangent inverse of the tangent, and that's equal to tangent inverse of 1/3. Well, the tangent inverse of the tangent, that undoes each other, right? And so that's just going to be theta is going to equal to pi over 6, or you can call it 30 degrees. Now, if you take a look at our original schematic, we have a theta here and a theta here. So the optimal angle for the triangle here is going to be theta plus theta, which is 2 pi over 6. 2 times it's pi over 3, which is 60 degrees. So 60 degrees would optimize it. If that were 60 degrees, then that isosceles triangle would be optimized. And not only that, but because this side is the same length as that side, and so that this angle is congruent to this angle, right? Because these two sides are congruent. Then these also must be equal to 60 degrees too, which means it's actually an equilateral triangle. Okay, and that's that.